In this video, we're going to define the mutual inductance between two coils. Then we derive an expression for mutual inductance in the case of two nested coils. And finally, we work a practical example of mutual inductance by computing the induced voltage in an ignition coil. So to get things started, we're looking at two different coils of wire, and these have different lengths and radii and number of turns, but it doesn't really matter what the details of the coils are yet. The main point that we're interested in is what happens qualitatively when the current in coil number 1 changes, and we're going to assume that that current, I1, is increasing. So using our prior knowledge of solenoids, we know there's a leftward magnetic field in coil number 1, and that field is also fringing outside of the coil itself. And I'll post a link to my main solenoid magnetic field video if you need a refresher on the directions here. But just to clarify, these field lines are all diving into coil number 1 from the right, so they all have a leftward component. And here's a quick reminder of the field strength within a long solenoid. So that magnetic field strength inside a long solenoid is given by B equals mu naught Ni, where mu naught is the permeability of free space. The little n there is the number of turns per unit length in the coil, and then I is the current in the coil. Now, the main point I'm trying to make with that is just that the magnetic field strength is proportional to the current running in that solenoid. And with our current arrangement, we're not really talking about the field inside the solenoid, but our fringing magnetic field strength is still going to be proportional to the current running in coil number 1. So with I1 increasing, the strength of this leftward pointing field is increasing, and that means we get an increasing leftward flux through the turns of coil number 2. Now, remembering Lenz's law, coil number 2 is going to respond with an induced EMF that could drive current in the direction that would oppose the change in magnetic flux through its turns. And because we have the increasing imposed leftward magnetic flux through those turns, coil number 2 is going to try to create rightward flux with this induced EMF. So we'll just imagine the terminals of this coil are bridged so that an induced current can actually flow in coil number 2 and create some rightward induced magnetic field. Then we can infer the direction of the induced current corresponding to this solenoid field, and it turns out to look like this. So it's flowing down the near face of the coil in the opposite direction of I1. Again, if the terminals of this coil aren't bridged, we aren't actually going to see this current, but we would still measure a voltage across the terminals attempting to move the current in this direction, and that's the induced EMF given by Faraday's law. And there's a quick reminder of Faraday's law, telling us that the induced EMF is proportional to the time rate of change in the magnetic flux through the turns of coil number 2. So the geometry of this setup makes a difference in how much EMF will be induced in the second coil when the current in the first coil changes. That induced EMF depends on how close the coils are and how many turns they have and what their diameters are, because all these things affect the magnetic flux through the turns of coil number 2. And to quantify how tightly linked these coils are by magnetic flux, we define their mutual inductance. So we say E2, the induced EMF in coil 2, is equal to negative M21 times the rate of change in the current through coil 1, that's di1 dt. So M21 is called the mutual inductance affecting coil number 2 due to coil number 1. And the minus sign is just there to remind us that the induced EMF acts in the direction that opposes the change in magnetic flux. Now, the whole reason this statement is reasonable is that we know from Faraday's law that the induced EMF is proportional to the time rate of change in magnetic flux, and we know the magnetic flux is proportional to the current in coil number 1 because the field generated by that coil is proportional to its current. So now we can imagine turning this around so that a changing current in coil number 2 induces an EMF in coil number 1, and we can write down a similar expression. So we say the induced EMF in coil number 1 is negative M12 times di2 dt. So there the mutual inductance is for the effect on coil number 1 due to a changing current in coil number 2. And again, that induced EMF in coil number 1 is proportional to the time rate of change in the current through coil number 2. Now, as it turns out, these mutual inductances in either direction, M12 and M21, are actually always exactly equal to each other regardless of the coil configuration. So we can just call the mutual inductance M in either direction, and we don't prove this fact in introductory physics, but I'm going to motivate it by calculating mutual inductance in each direction for two nested coils just to show that it works, at least as long as we're willing to make long solenoid approximations. Now, one last thing before we work that example. When we introduce a new quantity, I like to take a look at its units. So there's our basic statement for mutual inductance. We have an induced EMF E2 is equal to negative M times the time rate of change in the current in the other coil, so di1 dt. So if we take a look at the units on both sides of this equation, induced EMF has units of volts, and then the time rate of change in the current, that's going to have units of amps per second. So we can go ahead and solve that for the units of mutual inductance. And when we do that, we find that the units of mutual inductance are volt-seconds per amp. Now, there's another way this is commonly expressed, and we can get to that by using Faraday's law again. So there's Faraday's law telling us that an induced EMF is proportional to a time rate of change in a magnetic flux, but magnetic flux is measured in Tesla meters squared. That's magnetic field strength multiplied by area, and then the time derivative gives us seconds in the denominator. Well, if we multiplied both sides of this by S, we would find that volt-seconds are actually equal to Tesla meters squared, and we can replace that up here, and we find that the units of mutual inductance are Tesla meters squared per amp. Now, this gets a special name. That's just a capital H, and the units of inductance are called henries. Now, in practical situations, we're usually dealing with inductors that have inductances on the order of millihenries, and we'll actually see that in our ignition coil example. So let's take a look at an explicit calculation of mutual inductance for two nested coils. So in this problem, we're told that we have two nested solenoids. Each has a different length. I just labeled those as L1 and L2. They have different cross-sectional areas. So one of these is long and skinny. It has a smaller cross-sectional area than the short and fat one. And we're asked to use the long solenoid approximation to explicitly compute the mutual inductance in each direction, and then finally show that those two mutual inductances are actually equal. So we're going to start by imagining a changing current in coil number one. That's the long skinny one. So there it is. I have a current flowing up the near face of this coil, and we're going to assume that current is changing, and that should induce an EMF in coil number two. So starting with the definition of mutual inductance, the induced EMF in coil 2 is going to be negative M21 times the rate of change in the current in coil 1. So that's di1 dt. And to find that M21, remember that's the goal of the problem, is to calculate the mutual inductance. We need to explicitly calculate the induced EMF in coil number 2 by using Faraday's law. So there's Faraday's law. Our induced EMF in coil number 2 is the negative of the rate of change in the flux through coil number 2. So the plan is to express the induced EMF as a time rate of change in magnetic flux, set that equal to the negative of M21 times di1 dt, and then we'll be able to solve for the mutual inductance M21. And in the process, we're going to see that the induced EMF is actually proportional to the rate of change in the current in coil number 1, which justifies the whole idea of defining inductance in the first place. Now, to make it a little easier to see the magnetic flux through coil number 2, there's the field lines generated within coil number 1 as that current I1 flows up the near face of the coil. And it's critical to see that only an area of A1 is covered by those field lines. So our magnetic flux is only going to use the area inside coil number 1, since not all the area inside coil number 2 has a magnetic field passing through it. So we go ahead and start by equating the right-hand sides of these two equations, and we'll just cancel a minus sign as we go. So on the left-hand side, and this came from Faraday's law, we have the time rate of change of the magnetic flux through coil number 2. And on the right-hand side, we have this mutual inductance multiplied by the rate of change in the current through coil number 1. Now remember, magnetic flux is the magnetic field strength multiplied by the area. So our field strength is given by the long solenoid magnetic field approximation, and that's this part right here. It's mu naught times N1 times I1. So that little N1 is the turns per unit length in coil number 1. And then I1, of course, is the current that happens to be flowing at the moment in coil number 1. So that's our field strength. But then our area over here is a little bit tricky. So we had to multiply by N2 because this flux is passing through big N2 number of turns in coil number 2. But we're using the cross-sectional area from coil number 1, and it's because this magnetic field inside coil number 2 is not filling all the space inside coil number 2. The magnetic field exists only inside that cross-section inside of coil number 1. So in the next step, we're going to pull all the constants out from the time derivative, and that's everything except for I1. That's the only thing that's time varying. At the same time, I'm going to replace this little n1 with the total number of turns in coil number 1 divided by its total length, because that little n stands for the turns per unit length. So again, the big N up here divided by the little L1 in the denominator, that's actually what used to be called little n1. So we get all the constants out in front, and that's mu naught times big N1, big N2 times A1 divided by the length of coil 1, that's little L1. The only thing left that was time varying is I1, so I have the time derivative of I1 there. And note at this point that we've shown using Faraday's law that the induced EMF in coil number 2 is indeed proportional to the time rate of change in the current in coil number 1. And that was the whole idea of defining mutual inductance in the first place. So that's a win. And now we cancel the dIdt's on both sides, and we'll turn things around. And we solve for our mutual inductance, M21. That's the effect on coil number 2 caused by coil number 1. And it turns out to be mu naught times big N1, big N2 times A1 over little L1. And again, we're keeping the directionality on the mutual inductance temporarily, but we've been promised that if we look at the other direction of mutual inductance, it has to come out the same. So now we're going to turn this process around, and we're running a current in coil number 2. I just called it I2, running up the near face of that coil. And we're going to compute the induced EMF in coil number 1 and use that to find the mutual inductance in the other direction, which we call M12. So there's the magnetic field lines inside coil number 2, and I want to point out immediately that some of those are not captured as magnetic flux through the turns of coil number 1, because the way we set this up, coil number 1 is skinnier than coil number 2. So again, we write down the definition of mutual inductance for the EMF induced in coil number 1. So we have E1 is negative M12 times the time rate of change in the current in coil number 2. And we write down Faraday's law. We know the induced EMF in coil number 1 is going to be proportional to the time rate of change in the magnetic flux captured by the turns of coil number 1. And again, we just set these two EMFs equal to each other, and we arrive at a similar expression to last time. We have the time rate of change of the flux captured by coil number 1 is equal to M12 times the time rate of change in the current through coil number 2. Now this time when we look at the details of the magnetic flux, things get really tricky. So again, magnetic flux captured by coil number 1 is going to be given by field strength multiplied by area. And the field strength part is this first group right here. It's mu naught times little n2 times I2. It's just our basic long solenoid approximation. And remember that little n2 stands for big N2, the total number of turns in the coil, divided by L2, the length of the coil. So we'll have to make that substitution later. Now we need to take that magnetic field strength and multiply by the area that it applies to. And for each turn of coil number 1 that field is passing through, the area is given by big A1, not big A2, because the turns of coil number 1 are what matter here. So that's actually a smaller area than the cross-sectional area of coil number 2. But the really tricky part is this part out in front, L2 over L1 times N1. So the issue there is that if I look at my diagram, the field generated by coil 2 is not even passing through all the turns of coil number 1. It's just the turns that happen to be covered by coil number 2. So I had to compute that number of turns by taking the total number of turns in coil number 1, that's big N1, and then I multiplied by this ratio L2 over L1. That's the ratio of lengths for the short coil to the long coil. So that's essentially giving me the percentage of the number of turns in L1 that are actually experiencing magnetic flux. So with all that trickiness explained, we can once again factor all the constants out of this time derivative. The only thing that's varying with time is I2. And as I factored the constants out, I replaced little n2 with big N2 divided by L2, because little n means the number of turns per unit length. And again, this whole expression, L2 over L1 times N1, tells you how many turns we're actually experiencing magnetic flux here. It was only a percentage of the total number of turns in coil number 1. And we're using the area corresponding to coil 1 because, again, the turns of coil number 1 are what's capturing flux here. And once again, we discover that the induced EMF in coil number 1 is going to be proportional to the time rate of change in the current in coil number 2. And that shows that this whole idea of defining mutual inductance in terms of a time rate of change in the current in the other coil actually makes sense. So once again, we cancel out the time rate of change in the current in coil number 2, and we're going to cancel a factor of little L2 while we're at it. And we turn things around to solve for M12. And it turns out, as promised, it turns out M12 is the exact same expression. That's mu naught big N1 big N2 times A1 divided by little L1. It's the exact same expression we got by going the other direction by using coil number 1 to induce EMF in coil number 2. Now, to be fair to those of you with a strong inner skeptic, you could rightly complain that the calculation we just finished misses the magnetic flux caused by the fringing field outside the shorter coil number 2, which should boost the total flux captured by the turns of coil number 1. This is a totally fair complaint, and there's some hidden sloppiness in here from using the long solenoid approximation. I can assure you that mutual inductances are actually the same in either direction, and if you're interested in the more advanced physics here, what you want to look for is the Neumann formula. That's spelled Neumann, and you'll find that in any upper division electrodynamics textbook. And really the proof that mutual inductances are the same in either direction is because of a symmetry in the Neumann formula. Okay, so now that we've established the idea of mutual inductance and calculated it in both directions for a pair of nested coils, let's find out how the ignition coil works for a gas motor. So here's the setup for our problem, and we've made a couple simplifying assumptions here. So we're told an ignition coil is formed from two nested coils of approximately the same length. So we gave them a length of 10 centimeters. And they have the same diameter. We said that's 4 centimeters. We're told the outer coil has 100 turns of wire in it, and then the inner coil has 5,000 turns. And by the way, this big difference in the number of turns, the whole point of that is to amplify the amount of induced EMF we're going to get. So we're told a current is running in the outer coil, and I showed that as I1, but it's suddenly disrupted. And this causes a rapid decrease in the current, and we're going to say the rate of decrease is actually 10 to the 6th amps per second. So we're not talking about an outer coil that's carrying millions of amps of current. The point is the rate of change is huge because we took an ordinary current and we cut it off so suddenly. So in part A, we're asked to find the mutual inductance of the coils, and we're just going to use the formula that we just derived for nested coils. So I'm just going to call it M here. And remember, M was mu naught times big N1, big N2. And then we had an A1 in our formula, but both of our coils in this example have approximately the same cross section. So I'm just going to call that A. And then that's all divided by the length of coil number 1. But again, we simplified it here, so each coil has the same length. So I'm just going to call that L. So when we sub in all the numbers here, and I don't really have room to show all the units, so you'll just have to trust me on that, we get for the permeability of free space 4 pi times 10 to the negative 7. The number of turns in the outer coil was 100. The number of turns in the inner coil was 5,000. And then for the cross-sectional area of these coils, we can write that directly in terms of diameter. It's 1/4 times pi diameter squared, and the diameter has to be written in SI units. So that's 0.04 meters. That's 4 centimeters, all squared. Now we have to take this and divide by the length. So the length was 10 centimeters or 0.1 meters. And when we run the numbers on this to 3 significant digits, we get 0.00790 henries for the mutual inductance between these coils. And again, millihenries are really typical for practical inductors, so it's common to express this in millihenries. I have 7.90 millihenries. So here's the part we're really interested in, and that's finding the induced voltage on the inner coil. So again, we've taken a coil with very few turns in it, and we just suddenly cut the current off. And that's going to make the rate of change in that current huge, which should increase our induced voltage. So we look at our basic definition of mutual inductance, and I don't care about the direction here, so I'm just going to say the absolute value of the induced EMF is given by M times the rate of change in the current through coil number 1. So our mutual inductance turned out to be 7.90 millihenries, and then our rate of change in the current for the outer coil was 10 to the 6th amps per second. So this gives us to 3 significant digits, 7,900 volts of induced EMF, which we could just write as 7.9 kilovolts. And this is actually the standard mechanism that's used on gas motors to generate a high enough voltage to create a spark across the gap in a spark plug, which then ignites the fuel. In the next video, we're going to compute the self-inductance of a coil. And coils have self-inductance because changing the current in a coil changes the magnetic field in that coil, but then that change in magnetic flux is resisted by an induced EMF that acts to slow the change in current. This sounds like it would give us turtles all the way down, but the calculation actually isn't that bad. I'll post a link to that video at the upper left, and I'll see you there.